So a queue in computer science is similar to a stack. A stack is a data structure where you can only put things on at one end and take things off from the same end. A queue is a data structure where you can only put things in one side at one end and take them off the opposite end. So where a good real world illustration of a stack would be a stack of plates in a cafeteria, for example. A real world example of a queue that typically comes to mind would be people standing in line. People standing in line at a grocery store looks a little differently these days than it did a year ago. People standing in line at a movie theater like we used to do, that sort of thing. Because in that situation, the first person who gets there is the first person who gets processed, right? So like a stack was last in, first out, a queue is going to be first in, first out. You put things at the back of a queue, otherwise known as a line, right? When you line up at the grocery store, you could also call that a queue, particularly if you are in Britain, right? Same thing. But when you put things into a queue or a line, you put them at the end of the line. And when you take things out of a queue or a line, you take them from the front of the line. So first in, first out. So that's basically the idea. You could pretty much, we could just go home now and you could probably take it from there. You could probably implement a queue using an array or a linked list, just knowing that so the difference between a stack and a queue is that instead of taking things from the same end that you put them on, you take them from the opposite end, right? That's the only difference. But let's go ahead and look at some queue operations. Test whether a queue is empty, add a new entry to the back of the queue. So we're going to call that push. Remove an entry from the front of the queue. We're going to call that pop. Get the entry that was added earliest to the queue. That's just kind of a funny way of saying get the entry that is at the front of the queue, right? And so that would be what we called top when we were working with stacks. Hold on just a second here. So let's actually go take a look at what the STL calls these operations just for a minute here. So give me a second. I guess I will just share the desk. Okay, so as you all probably remember, I like to go to c++.com for this information. Containers, queue. So here's the list of member functions. Empty is the one that tests whether the container is empty or not. Size was not mentioned in the textbook, but STL supplies it. Front allows you to access the next element, so that would be sort of like our top operation in the stack. Interestingly, the STL is also going to allow you to access the last element in the queue. That's not necessarily an operation that you would have in a sort of classical computer science queue where you only take things from the front of the queue. But there you have it. just hope that the grocery store clerk doesn't use that operation and start taking the last person who got in line first. And then push is going to be inserting the element at the back of the queue, and pop is going to be taking an element from the front of the queue. Okay, so the most important ones here are front, which is sort of like our top operation with the stack, and then we've got push and pop, just like we did with stacks. Yeah, something like that. Okay, any questions about that? You can go back to the textbook. Just wanted you to see how the STL handles that situation. Okay. So here's just another statement of the abstract, the specification of the abstract data type. They're going to call it in the front. We're going to call. Let me try that again. In the text, we're going to call what STL calls push. We're going to call that NQ. We're going to call what STL calls pop. We're going to call that DQ, or DQ. And what the STL calls front, we're going to call peak front. Okay, so just different names for the same things. Just another way of saying the same thing again here now. And then here's an example. If we put in a 5, now we put in a 2, so it's going to look like this. So 5 is at the front, 2 is at the back. Then we put in a 7, so we've got 5, 2, 7. Then if we say peak front, that's going to give us the 5, but it doesn't change the queue. Then if we call DQ, that's going to take the 5 out of the queue, so we're left with just 2 and 7, with 2 at the front. If we DQ again, that's going to take the 2 out of the queue and leave us with just a 7 in the queue. Any questions so far? All right, let's do this. If you add the letters A, B, C, and D in sequence to a queue of characters and then remove them, in what order will they leave the queue? Don't everyone jump at once. Yeah, that's right. Same order you put them in, right? What if it was a stack? What order would they leave the stack? Reverse, right? Okay. All right. At the risk of being too simple here, I guess I should just take the time and actually do this right. So let's work this out. After I call NQ1, my queue is going to look like this. And then I NQ a 2, so it's going to look like this. Then I NQ a 3, then I NQ a 4. The 1 is at the front, right? The 4 is at the back. So when I call DQ, that means take the 1 off the front. Then I say Q front gets, oh, sorry. Let's start that over again. I just realized that there were 2 different queues going on here. Oops. So here's Q1. And here's Q2. So Q1 dot in Q1. Q1 dot in Q2 means that. Q2 dot in Q3 means that. Q2 dot in Q4 means that. Q1 dot DQ means take the 1 from the front of Q1. Q front gets Q2 dot peak front. So now we're going to have a variable called Q front, and it's going to be equal to 3. Everyone okay so far? So now Q1.enqueue 3. So that means I'm putting the 3 up here. Then Q1.enqueue5. Then Q2.dequeue. Then Q2.enqueue6. Okay. Anybody want me to go over that again? All right. So here's our interface for queues, just like we had an interface for bags and an interface for sets and an interface for stacks. And I think there was also an interface for lists, but we didn't really do much with it in this case. And just on that note, as a digression, just for a second, the reason we didn't do that much with it is that the interface for a list is much less standardized than it is for a lot of these other ADTs, right? Like the queue and the stack are pretty standardized, just except when they call the function something slightly different. Not so much with lists. Lots of different options. Anyway, so there's nothing too surprising here, I don't think. This is the actual C++ code for the interface. Okay, so one of the big major applications of queues that probably most computer scientists think of right away when they think about what a queue might be used for is doing a simulation. So, for example, in the assignment that you guys are going to be working on this week, you're going to be doing a simulation about people arriving at a bank, getting in line, being served by the teller, and then leaving. And so we're going to run a simulation just to see like how much time people spend waiting in line and things like that. Excuse me. Hopefully you can see how a queue would be related to that, right? Because there's going to be a line of people in the queue. You're just going to have a queue filled with customers. I'm not going to talk about these. These are basically, he's going to go through some applications of the ADT queue. So we're going to skip over that for now, and because we're going to come back around to that. But let's talk about priority queues. So a priority queue is just like a queue, except that the items in the queue get assigned a priority. And so the first item in the queue or the front item in the queue is not necessarily the first item that got put in. Instead, it's the item in the queue that has the highest priority. So when you enter something into the queue, you give that item a priority so that the priority queue abstract data type knows what item to return when you ask for the next item. Anybody want to ask a question about that or have me say that again? So let's go back to
Something happened to your audio that we can't hear you anymore.
Can you hear me now?
You covered up
Yes.
the mic. Yeah.
Maybe I must have like put my hand down on the microphone or something. Better now?
Yes.
Okay, thank you for letting me know. Now I'm like nervous where I put my hands. Um, okay, so here are our member functions. And really, one pretty good way of understanding the functionality of a container class, such as a priority queue, is to just look at some member functions, make sure you understand what they're doing. The main ones here are top, push, and pop. So that's the same as a, a regular queue, except just instead of front, we have top. And with priority queues, top means the item with the highest priority. Okay, so you can imagine a data structure where you push things into the data structure, you take out the item in the data structure that has the highest priority, or you look at the item in the data structure that has the highest priority. And that's all you have access to. Okay. Okay, let's go back and look at the text a little more. So here's how the text is going to describe the operations. Add a new entry to the priority queue in its sorted position based on priority value. Okay, so we're not going to worry too much about that for now in terms of the implementation. All we really care about now is that when I call the top function or the pop function, I have an easy way to find which item has the highest priority. So we've got add a new entry, remove the entry with the highest priority value, or return the entry with the highest priority value. Basically, three important operations there. Here's our, just saying the same thing another way. Instead of push, the text is going to call it add. Instead of pop, the text is going to call it remove. Instead of top, the text is going to call it peak. So you notice in the standard template library, one of the philosophies is let's use the same terminology across the different containers whenever possible, right? So you see push and pop on a lot of them. Anyway, in the text, it seems a little bit more like it's almost a conscious effort to choose different names across the different containers. Okay, here's what I want to do. This is another application example using a priority queue, but I want to jump ahead and talk about a particular simulation that we are going to be working on, which is this simulation here in 13.4. So I kind of described this already. Let me, I guess I can just read it. Sorry, let's keep having to adjust my window here. Okay, all of this stuff leading up to it. What I really want to do is I just want to dive in and talk about the simulation a little bit. Where did that go? I'm actually looking for All right, let's look at figure 13.8 and see what's going on here. So what this means here, and this is actually going to be the data that you're going to be reading in your assignment this week, is that at time 20, someone enters the queue. Actually, I don't remember what the 6 means. Anybody catch that? Length. So that would be how long the transaction is going to take. Okay, so the duration of the transaction. So when this person when this person who is arriving, this customer arrives at time 20, whenever they eventually get up to a teller, their transaction is going to take 6 units of time, whatever it is we're talking about, probably minutes, I assume. So you can see here that we've got these 4 items here, and what we're going to do is we're going to start by just putting these 4 items into a priority queue. Okay, so you can see that the 26 here, the A stands for arrival because this is an arrival event. And so there's an arrival at time 20 that's going to take 6 minutes. There's an arrival at time 22 that's going to take 4 minutes. There's an arrival at time 23 that's going to take 2 minutes. And there's an arrival at time 30 that's going to take 3 minutes. And so the first step in our process is going to be just reading the input file and putting those elements into a priority queue. Now in this case, they've got the front and back here, but what matters is the priority, and how the priority is going to be determined in our case is the arrival time, right? Whatever the time of the event is, the earlier that is, or the lower the number that is, the higher the priority that event is going to have. Does that make sense? Because, you know, if someone comes into the bank at time 20, obviously they're going to have a higher priority than someone that comes into the bank at time 22. Okay, so now we're going to start processing. The first thing that happens is we process this arrival, and since there's a teller available, we know that this person is going to depart at time 26, right? Because they arrived at time 20, there's a teller available, they walk right up to the counter, their transaction takes 6 minutes, so they're going to depart at time 26. So what that means is we're going to create a new event, which is going to be a departure event. And we're going to put that into the priority queue. And since the departure time is 26, that departure event is going to go right here in the priority queue between the 23 and the 30. Okay? Does that make sense? And the departure doesn't have a duration, so we just put a dash there. Any questions so far? Okay, so moving on. At this point, what I do is I say, okay, priority queue, give me the next event or give me the event in your queue now that has the highest priority. So the priority queue is going to say, it's this one here, arrival time 22, duration 4. So I have to process that event. At this point, there is not a teller available. We're just keeping it simple, and we're going to assume there's only one teller. So at time 22, the teller's not available yet, right? So what happens is we're going to put that event into line at the bank. So this queue over here on the left, which is called bank queue, is just going to be the line of people standing there waiting to be served by the teller. And so at time 22, what we have is we have one person standing in line, and we have 3 events that we have yet to process. Okay? So backing up and explaining that step one more time, I'm going to say when the element in the priority queue that has the highest priority is an arrival event and there's no teller available, the action we take is we put that event into the bank queue. Okay? Now, let's see what happens next. We say, okay, priority queue, give me the next element or the element in your priority queue that has the highest priority now, and that's going to be this arrival event at time 23. There's still no teller available, so we're going to put that event at the back of the bank queue. So just to be clear, this thing on the left here is a regular queue. This thing on the right here is a priority queue. Okay, so now we're at this picture here that has the 23 on the left. And so now we say, okay, okay, priority queue, give me the item in your priority queue that has the highest priority. And what we get back is this departure event that says there's a departure at time 26. And now notice in our minds, we're thinking, we're pretty smart. And so we think, oh, I remember that got put there because we had someone who arrived at time 20 and their transaction took 6 minutes. But the algorithm doesn't care about that. The algorithm just knows, okay, this is the next highest event, the event in the priority queue that now has the highest priority, so it's what I'm going to process. So there's a departure at time 26. There are people in the bank queue. There are events in the bank queue. So that means that what we need to do is take the first person, the first event in the bank queue, or another way of saying that is the event at the front of the bank queue, and process it, which means just we're going to remove it from the bank queue, and we're going to create a departure event for when this person is done being processed, right? So this event that has an arrival time of 22 actually got started being processed at time 26. So we create this departure event over here that says, okay, there's going to be a departure event at time 30. 26 plus 4, because the duration on this guy was 4. Okay? So to say that again, if we have a departure event, the action we take is we pull an event from the front of the bank queue and we process it by creating a departure event and putting that departure event into the event list priority queue. Okay? All of the stuff that I'm saying you're going to see in pseudocode in just a minute, but let's keep going. Now at this point, I say, okay, now Mr. or Mrs. event list priority queue, give me the item in your priority queue that has the highest priority, and that's going to be this one here. At this point, it could be either one, right? And I don't think it matters. We're just going to go ahead and take the arrival event. There's an arrival at time 30. So we take this arrival event and there's no teller available at this point. So we put the event into the bank queue. And then now still sitting, we're kind of doing two things at the same time here. So that's what we do with the um, arrival at time 30 event. But we're also going to process the departure at time 30 event. So this is actually going to be two calls to the priority queue, right? The first one was gave me the arrival event at time 30, and then I'm going to call the event list priority queue again to give me this event, which is a departure at time 30. And so when we process this departure at time 30, what happens is we are going to take this event from the front of the bank queue and create a departure event from it. So it's time 30, and we know that this event has a duration of 2 minutes. So that means we're going to create a departure event at time 32. Don't worry, I think that, so the pseudocode is going to like formalize all of this stuff that I'm saying. So you don't have to memorize all the steps. And then one more step to go, right? At this point, I'm on the line that says 30 on it, and I say, okay, priority queue, tell me what the item in your priority queue is with the highest priority, and it gives me this departure event. When we have a departure event, what happens is we take the event at the front of the bank queue and we process it because it's now time 32 and this has a duration of 3. What happens is we create a departure event at time 35 and put it in the priority queue. And then technically there will be one more time through the loop where we will process this departure at time 35. Okay, so what I want to do is let's look at the pseudocode a little bit, and then I'm going to actually trace through one of these with you step by step. And in your homework, the way I've set it up is part 1 of your homework is to actually do one of these simulations yourself. And then step 2 is to actually write the code where you're going to translate the pseudocode into actual code.